Hi, I am Vidushi Goyal from University of Michigan. In this presentation, I will be talking about our work Nexus and Interconnect for heterogeneous system in package architectures. The plot here shows cost to develop a new chip, and we see it's increasing exponentially as we move to more sophisticated technology nodes. This means for a startup to build a new SoC or chip requires investment of hundreds of millions of dollars, whereas a software startup like Instagram was up and running with just few hundred Ks. This is because of the vast open source software platform available, whereas in hardware industry, lot of information is proprietary, which makes the development cost very high. This is the motivation behind exploring the system in package platform to reduce this one-time development cost. The first question to answer is why should we use SIP over SoC? SoC or system on chip are big and expensive monolithic chip which are restricted to single technology node with almost no flexibility. Whereas SIP system in package are assembly of many small chiplets which support multiple technology nodes and the system is more modular and flexible. There are many advantages of SIP over SoCs. For SIP, a single IP can be developed in isolation and plugged in different domains. However, due to monolithic nature of SoCs, same IP needs to be developed and integrated for each domain. Thus, IP reuse across domain is cheaper for SIP as compared to SoC. Next, on migrating to a newer version of SoC, say in 28 nanometer, all IPs needs to be migrated from 45 to 28, whereas for SIP we can selectively migrate only few IPs to 28 nanometer. One of the biggest advantages of SIP is its yield. SoC being a big chip has lower yield as compared to SIP made of small chiplets with higher yields. Finally, since SIP involves cutting down on development steps, the time to market is less for SIP as compared. Motivated by the potential of SIP to replace SoC, we designed an interconnect architecture for SIP platforms. The design goals which we want to achieve for interconnect architecture is to be modular and at par with SoC performance. The interconnect layer or architecture should leverage several interposer properties like high bandwidth, low delays, and signal attenuation. Finally, we want to map the interactive mobile SoC applications on a proposed interconnect architecture. However, there are some design constraints that needs to be addressed. Microbumps with a pitch of 40 to 50 micrometer occupy area and are expensive. They restrict the minimum chiplet size so as to be able to support large microbump ports. Our proposed architecture provides two solutions to reduce microbumps. We use Minichains and embed Cirrus logic at chiplet interface, which are discussed in details in following slides. In this work, we propose Nexus, comprising of interconnect chiplet and Minichains. It's a hub and spoke architecture with a dedicated interconnect chiplet that keeps the modular property of SIP and allows plug and play with chiplets, replacing one chiplet at a time. Within the interconnect chiplet, there is a flexible router network which is determined by user during design time. The router at edge or edge routers connect to the IPs via network interface and microbumps. However, having dedicated port for each chiplet will blow up the size of interconnect chiplet. Therefore, to reduce the number of chiplet ports, we chain few chiplets that share same port on interconnect chiplet, which are called minichains. The IPs in minichains can communicate directly using high bandwidth interposer communication channels. Topologically, minichains are unidirectional with the path of communication being determined by the forward receive bits at each chiplet. When a forward bit is set, the IP forwards the incoming data to the next IP and vice versa. These F and R bits are set by the edge routers at the interconnect chiplet. The edge routers maintain a flow status bit or table to track availability of source destination links of the attached mini chains. Depending on this availability, it sets F and R bits for an incoming request. For example, in case where IP2 wants to talk to IP1, IP2 sends a request to interconnect IP. Based on the flow status bits, interconnect IP sends the F and R set signals to all the IPs on data path. Once the set signals are received, IP2 starts transmitting data to IP1. When the data transmission is complete, the destination IP sends a release signal to reset the entries in flow status table. The next task is to tailor the modern SOC applications to map efficiently on Nexus. We find that in modern application, IPs communicate via memory where the preceding IP writes its output to memory and the following IP reads those results as input. Therefore, there is a lot of back and forth of data movement with memory being used as buffer. We see an opportunity for an optimization here. Instead of having a zigzag data path, we can utilize the direct path and high bandwidth links supported by Minichains in Nexus, where IPs talk directly to next IP in the Minichain rather than communicating via memory. In the conventional system, arrows 1 and 2 represent expensive data transfer using memory as buffer. In Nexus, it is replaced by a direct arrow connecting IP1 and IP2 over Minichains. In this way, we save on expensive memory reads and writes and reduce interconnect bandwidth requirement. But there are some fundamental issues which we have to address for the direct IP to IP communication. The applications can have high buffering requirement. Frame processed by first IP needs to be stored before second IP starts working on it. This buffering requirement can be as high as 25 MB for video applications. Hence, we use subframing in Nexus. Subframing breaks down the full frame into smaller chunks. The video images can be broken down into pixel blocks, and the audio frames can be broken down into small independent frames. We use a subframe size of 1 KB, which reduces the buffer requirements to just few KBs, and processing is done at subframe granularity in a pipeline fashion across multiple IPs. We evaluate Nexus in three ways: network evaluation, application evaluation, and cost evaluation, which we'll discuss in detail. Our evaluation framework is built upon GemDroid and BookSim. GemDroid uses Gem5 CPU model, analytical IP models, DRAM Sim2 models, and BookSim is used for network simulation. We integrated Gem5 and BookSim to get cycle accurate closed loop full system simulation. Raw application traces were collected from Android emulator by running various workloads on the emulator. As for workloads, we used popular audio-video mobile applications. This table lists design parameters for Nexus like number of chiplets, size of interconnect chiplet delays, and so on. The goal of network evaluation is to find the best topology for router network in the interconnect chiplet for various traffic patterns. Here, we compare various topologies for interconnect chiplet against SoC with popular NOC topologies. We find that Nexus with crossbar interconnect chiplet is at par with other NOC topologies like mesh, compared to which It has 57% lower latency and is within 6% of its bandwidth. Another important comparison we do is with Buterdonut, which is a SIP topology aimed for homogeneous multi-core traffic. We find that as expected, for uniform random traffic simulating multi-core traffic, Buterdonut beats all other topologies, including Nexus with crossbar. However, in this work, we focus on heterogeneous SOC application with pipeline traffic pattern. For a synthetic chain traffic, we find that Nexus with crossbar gives lowest latency and highest bandwidth over other competitive SOC as well as Buterdonut topology. Moreover, as the packet size increases, which is the case for data intensive SOC application, Nexus advantages over other topology increases. Hence, from topology exploration, we find that Nexus with crossbar and Minichains provides better performance than regular or specialized homogeneous NOC architectures for pipeline data flow traffic. We also evaluate Nexus using real-world application traces of various audio-video SoC applications. There are three configurations that we compare. The first one is direct IP to IPs, where IPs talk directly to each other. There is buffering via buff configuration, where the data is forwarded from an infinite buffer placed at memory controller, thus removing all memory-related bottlenecks and only exposing network issues. And the baseline VMM, where data is read and written from memory. We compare two SIP networks, Nexus, a proposed solution, and Buterdonut, a competitive and a state-of-the-art chiplet-based network. The plot shows the application bandwidth served by various network and configuration. On looking closely into YouTube and audio-video application, we see that Nexus with direct IP to IP is able to serve a highest bandwidth of 31 Gbps, which is higher than Buterdonut with direct communication or direct IP to IP. However, if we look into audio record application, we find that all the configurations are able to serve very similar bandwidth. This is because audio applications have small frame size and require less bandwidth. The bandwidth results translate directly to performance result, where performance is number of frames completed. Nexus with direct IP to IP communication would give a performance improvement of 4x on average over Nexus VMM. For audio record, the performance is same across all configuration because of small bandwidth requirements. Finally, since Nexus bypasses memory as well as reduces data movement over network, Nexus with direct IP to IP communication reduces energy per bit as compared to VMM and VBuff configuration. Overall, Nexus with IP to IP communication provides 88% energy reduction over VMM configuration. Next, we show some results on impact on the cost of building an SIP over an SoC. For analysis, we show only the impact of mass cost, one of the major contributor and attributing to 50% of total cost, while keeping other factors the same across the two platforms. We observe that for a 90% reuse factor, which means 90% of IPs are obtained off the shelf and only 10% are developed from scratch, SIP reduces NRE or one-time cost by 1.8x. This cost reduction increases to 3.5x as we move towards newer technology node. In summary, we propose Nexus, an interconnect architecture for SIP that consists of a dedicated interconnect chiplet and mini-chains. We observe that Nexus with crossbar interconnect chiplet topology is at par with popular NOC mesh topology. We also demonstrate chaining in mobile applications and show that they can utilize the direct communication link of mini-chains rather than using memory as buffer. Finally, Nexus with IP to IP communication provides 28% performance improvement and 31% energy savings over state-of-the-art Buterdonut SIP architecture. Thank you for listening to the talk. If you have questions, please refer to the paper for details or contact us via email.